In this video, we will do a Fundamental Theorem of Calculus Part 1 example. So in this example, we have this graph of a function y equals f of t, and we're going to let g of x be an area function. It's the definite integral from -2 to x of f of t dt. So in part A of this example, it asks us to find the intervals where the function g is increasing and decreasing. Okay, so one of the keys to be able to answer this is, so we can figure out when a function is increasing and decreasing by looking at its derivative. So I'm going to need to know what the derivative of this area function is. And that's where FTC part 1 comes into play. So in our previous video, we showed that if we have this area function g of x, which is the integral from a to x of f of t dt, then the derivative of that area function, g prime of x, is just the function in the integral, but replacing the t with an x. In other words, g prime of x is equal to f of x. Okay, so let's write that down here in our example. G prime of x equals f of x. So when is g increasing? Well, the function is increasing when its derivative is positive. And the derivative of g is just the function f. So when is the function f positive? Well, it's positive from x is -1 up until x is 6. So that's where g is increasing, on the interval from -1 to 6, since g prime of x equals f of x, and this function f of x is positive. The function f of x is positive on that interval from -1 to 6. So similarly, we would say that g is decreasing, let's put this in red, decreasing on the interval from -3 to -1, since the derivative of g prime of x, which we know is f of x, by FTC part 1, in fact, let me write that up here. I wrote that g prime of x equaled f of x. Let's write that this is by FTC part 1. Okay, so g prime of x equals f of x is, and f of x, the function f of x, is negative on this interval. All of the outputs, all of the y values on that interval are negative. And that's our answer for part A. So I also think it's important to have a conceptual idea of why this is true. How come this area function g of x is increasing when the function f is positive? And why is g decreasing when the function f is negative? So if we think about this area function, so it's the area under the graph of f from -2, so -2 is somewhere here, to some value x. So let's say that x was here. So x was here. So if we were looking at that area, we would be looking at this whole section, which was count as a negative area because it's below the x-axis, and this whole part. And at that x value, g is increasing because if we made x get a little bit bigger, if we moved x a little bit this way, so if I moved it a little bit that way, let's say I moved it to here, and now I looked at how did the area change? Well, I've added some positive area. We've added all of this. We've added some positive area that made the area function increase and get bigger. So that's going to happen when x is at a point where the function is above the x-axis, because I'm adding a positive area like we did here. So now I'm going to erase that. If on the flip side, x had been somewhere here, corresponding to a negative point on the graph of f, so a point with a negative y value, the area up until that point is this part, is all of this. And if we were to increase x a little bit, so if we were to increase x and move it a little bit further and look at that resulting area, so we might be somewhere here now. And if I look at that part of the graph, we have now added this area right here, but that counts as a negative area, which means my area function got smaller. Or in other words, g is decreasing. So that's going to happen when we're at a point x that has a negative y value like this one right here. Because if it's a negative y value, increasing x will result in adding a negative area. And that's why g is decreasing. All right, so I want to zoom it out now a bit so that we can look at part B of this example while still looking at the original graph. So B asks, now state the x values of the local maxima and minima of g. So this is some review from the previous calculus course. Okay, so a local min occurs where the function g changes from decreasing to increasing. And that's going to happen when the derivative changes from negative to positive. So there's a local min at x equals -1, because at x equals -1, g changes from decreasing to increasing. Because the derivative of g, which is f by the Fundamental Theorem of Calculus part 1, the derivative of g, which is f, changes from being negative to positive. And that's what makes g change from decreasing to increasing. Okay, so there's no local maxes because there's no place where g is going to change from increasing to decreasing. For that to happen, the derivative of it, which is this graph of f, would need to change from positive to negative, but that never happens. All right, so let's look at part C of this example now. C is going to ask, find the intervals where g is concave up and down. So again, this is some review from the previous calculus course. So remember that a function g is concave up. I'm just going to write cu for concave up. Concave up when the second derivative, so the second derivative of g would be the first derivative of f, because we're just taking this equation and doing the derivative of both sides. So the second derivative of g of x equals f prime of x. And g is concave up when the second derivative of g is positive. So we need to know when this is positive, and that's going to be true if and only if. So the symbol just means this is going to be equivalent to. I need to know when f prime is positive. So let's zoom it out so we can look at the graph. So that's the graph of f up there. And the derivative of f is positive when f of x is increasing. So we're looking for when f is increasing. And that happens on what interval? It happens on the interval from -3 to -1. And then also, so I put a union symbol, also on the interval from 4 to 6. So one thing I want to say about these is, just as a bit of review as well, is when we write these intervals of increasing, decreasing, and concave up and down, the convention is to use open intervals for increasing, decreasing, and concavity questions. So finally, let's write when g is concave down. So g is, I'm going to write CD for concave down. CD, whoops, is concave down when the second derivative, and the second derivative of g is f prime of x. So that needs to be negative. The second derivative of g needs to be negative for g to be concave down. Okay, so that happens when f prime is negative. And f prime of negative means that f of x is decreasing. And I can see when that happens by looking at my graph. By looking at my graph, f is decreasing on the interval from 2 to 4. And that would be my answer. That is when G is concave down, and this was the interval where G was concave up. So in terms of our goals for this section, we have finished our second goal, which was to do an example using FTC Part 1. And the next video will state what FTC Part 2 is and give a rough proof of it.